Bright QT. Every student matters.
Hello dear students, till now in magnetic effects of current we have studied about a straight current carrying conductor, a circular current carrying conductor, a solenoid, a electromagnet and a bar magnet, right? Now if some magnetic field produced with the current, through that magnetic field it is creating the magnetic lines of forces, so the opposite of it should also be true. That means a magnet should also exert an equal and opposite force on the current carrying conductor. So let us see through an activity. This is a setup that we are going to take. We have just taken a battery and we have connected a straight current carrying conductor with this battery, this A and B. Fine. Now because we want to see the effect of force on this particular current carrying conductor, what we did was, instead of taking a long connected wire, we just broke the wire from here and from this part, right, so that this part AB is free to move. It is connected through a support with a flexible joint out here, and here we have just taken two pieces, and in order to complete the circuit we have taken this particular container containing a metal mercury, which is a good conductor of electricity, right? Now we provided magnetic field through this horseshoe type magnet having the north and the south pole. Now very importantly, the moment we switch the circuit on, we will see that this wire AB is just pushed in the front side. This wire is pushed in the front side. The moment it is pushed outside this particular container, because now the circuit will be disrupted, therefore no current is passed and this wire will go back again to its original position. Mind you, the switch is still on. Fine. So the moment it will go back to its original position and come in contact with this metallic mercury container, once again the circuit is completed, once again there is current in the wire, and again this wire is pushed in the further direction, in the forward direction. So this particular activity shows that this magnet is exerting some force on this current carrying conductor, because of which this conductor is moving, right? Now with observations we find that this particular force which is applied is maximum. The force is maximum when the current carrying conductor is placed perpendicular to the magnetic field. Now this magnetic field is always from north pole to south pole, right? The magnetic lines of forces we have already studied that they always move from north pole to the south pole, right? So the force is maximum when the conductor is placed vertically perpendicular in this magnetic field, right? And if it is placed parallel, then in that case no force or negligible amount of force is observed. So the condition required for this particular straight carrying conductor to move or to change its position under the impact of the force, that is when it is placed perpendicular. Now in which direction this conductor will be moving, for finding that direction Fleming gave us a rule which is known as Fleming's left hand rule. Now students, this is very important. You need to relate that what exactly is this rule and what is the application. Now what Fleming said was, he said that take your left hand and you need to take the three fingers. This is the thumb, this is the forefinger and this is the middle finger. Left hand we are taking, we are taking these three fingers, the thumb, the forefinger and the middle finger, and he said that place these fingers perpendicular to each other like this. Please try to relate what I have made. Right now, this particular finger is perpendicular to this forefinger. So forefinger and middle finger are perpendicular to each other. Similarly, if we see this forefinger and the thumb, they are perpendicular to each other, and the thumb and the middle finger are also perpendicular to each other. As per Flemings, he said that take the thumb, the forefinger and the middle finger of your left hand in such a way that they are perpendicular to each other. Right? You can observe they are perpendicular to each other. Fine. Now, as per Fleming's left hand rule, if the forefinger points towards the magnetic field lines, and when I am saying that it is pointing towards magnetic field lines, means the magnetic field lines are from north to south direction. So this will be the north part, this will be the south part. So the tip is going towards south, right? North to south. Fine. And if the middle finger represents the direction of current, fine. In that case, I repeat, the forefinger pointing towards magnetic field lines, the middle finger points towards the direction of current, then the thumb will give us the direction of force acting on this particular wire, as to in which direction the force will be exerted, and obviously if the force is exerted in particular direction, then the particular wire is going to move in that direction only. So we can say that the force or the direction of motion is represented by the thumb. Now let us see what exactly Fleming said in his left hand rule. He said that place the forefinger, the middle finger and thumb of left hand perpendicular to each other. This is important, right? They need to be perpendicular to each other, right? If forefinger points towards direction of magnetic field lines, if the forefinger is representing the direction of magnetic field lines, which is from north pole to south pole, the middle finger represents the direction of current, then the thumb will point towards what? The direction of force, or we may also say that the direction of motion of the conducting wire. This is Fleming's left hand rule. Now this Fleming's left hand rule can also be applied by way of the fact that what we are saying is, if a current carrying conductor, this wire is placed in a magnetic field, then some amount of force will act on this wire and produce motion, right? This is the actual crux or the conclusion of Fleming's left hand rule. I repeat that if a current carrying conductor is placed in a magnetic field, then a force will act on this conducting wire and will produce motion in it. Yeah, of course, the condition provided is they are perpendicular to each other. and the important thing is the force which will be produced, that will be perpendicular to both the magnetic field as well as the direction of current. That is what we saw in Fleming's left hand rule. Right? Got it?